Hello everyone, this is Engineer on the Reel, and in this video we'll be continuing our discussion in structural steel design. In the last steel design video I posted, I discussed all about the compressive strength of an H shape that has a slender flange. That means the flange is too thin. Now here in this video, I'll be discussing an example how to calculate the design strength of a W shape that has a web that is too thin, okay, a slender web. And also we'll be calculating its nominal compressive strength and the LRFD design compressive strength and ASD allowable compressive strength. Well, let's discuss this first. Ito, the nominal compressive strength, Pn, shall be determined based on this formula, FCR times Ag, for a member with slender element. And here we'll be involving Q now in this limiting slenderness ratio for inelastic buckling. There's Q here, and also the FCR already has Q. So Q times 0.658 raised to QFY over FE. And if that KL over R exceeds this limiting value, then we're going to use the elastic buckling stress 0.877 FE. Now that Q is the net reduction factor accounting for all slender compression elements. So that's equal to the product of QS and QA. This QS is the reduction factor for the unstiffened element. That means that is flange of the W shape. And that QA is the reduction factor for the unstiffened element, and that is the web for the W shape. And if the flange is just non-slender, that means it's not too thin, no, then we must take that QS as 1. Okay, and if the web is too thin, then we're gonna solve QA using a formula. So this will be the formula that we're going to use. The reduction factor QA for slender stiffened elements. For the white flange, again, that is the web. QA is equal to the ratio of the effective area over the gross area of the W shape. And that effective area is the summation of effective areas of the cross-section based on the reduced effective width PE. The width that is mentioned here is the width of the web. And the reduced effective width is determined as follows for uniformly compressed slender elements with B over T greater than or equal to 1.49 square root of E over F. The formula is 1.92 T square root of E over F times 1 minus 0.34 over B over T square root of E over F. And that must be less than B. And that F is the FCR flexural stress calculated based on Q equal to 1, based on the formula that I showed in the previous slide. Okay? Well, dito, let's not include this anymore. This is for flanges of square and rectangular slender element. No? For the white flange, ito yung formula na gagamitin natin. Okay? So, again, ito yun. No? The BE is this, the effective width or length of that web. Yung exact width or height of the web is equal to this total depth minus twice of K or design K. That K is the distance from the outer flange to the web toe of the fillet here. Okay, so that is K. Ito yung K. So we'll be using this formula that B over T is H over TW. Okay, so this is the example. Determine the nominal compressive strength of a W360 by 44 of a 992 steel column having a length of 4 meters and is fixed at both ends. So Fy for A992 is 345 megapascal. So these are the properties, geometric properties. What we'll do first. The first is we have to check if the width to thickness ratio conform to the limiting values. So the width to thickness ratio of the flange is BF over 2TF, and that is equal to 171 over twice of 9.78, and that is 8.74. And for the web must have a width to thickness ratio equal to h over tw. And by the way, the limiting value for flange is 0.56 square root of e over fy. That is provided by the code. And evaluating that, we can get that to be 13.48. And that is greater than 8.74. So since this lambda, this width to thickness ratio doesn't exceed this, then we can say that the flange is not slender. It's either be compact or non-compact. Basta, it's not slender. And for the web, again, the web must be h over tw. And that h is the total depth minus twice of k. K here and k at the bottom. So that's 351 minus twice of 19.9 all over 6.86. So that gives us 45.36. And as we can see, if we compare that to this 1.46 square root of e over fy, that is the limiting for the stiffened element. This is stiffened by the flanges. So that is 35.87. This is less than 45.36. And that shows that this web is too long. And if that is too long, this would be dangerous to a local instability. This would be dangerous to local buckling. This would become like that. Now this would something like twist, because of the compression. Okay, because this is too long, or the thickness is too thin now compared to its length or to its height. Okay, so that's it. And continuing this, we can say that the web is a slender element. Okay, because this exceeds this, or this value is less than this. So with a slender web, we have to calculate Q sub A. Q sub S, the reduction factor for the unstiffened element, is just 1. And QA may be 1, but maybe less. Okay, so QA is the effective area over the gross area. And again, the formula for this is I showed kanina, no? And there's an F, and that F is the flexural stress calculated based on Q equal to 1. So let's calculate for FCR first, no? Assuming Q equal to 1. So checking for the limiting value of the slenderness ratio for inelastic buckling. This is 113.4. That's the formula, 4.71 square root of E over Fy. Okay, E is 200,000, Fy is 345. And if the KL over R of this column exceeds this, then we must use the elastic buckling formula, which is 0.877 Fe. But if it doesn't exceed this, if the KL over R of the column doesn't exceed this, then the formula is 0.658 raised to Fy over Fe times Fy, the inelastic formula. Okay, so the KL over R is 0.65 times 4,000 over R. This R, of course, must be the minimum radius of gyration, because there is no bracing within the mid-height. Okay, so the unbraced length is 4,000 millimeters. And if you have noticed, I used K equal to 0.65. Well, because that is the recommended design value of K if the ends are both fixed. Okay, theoretically it's 0.5, but if we are designing by using the AISC code or the NECP 2015 code, use the recommended values. Okay, so I'm using this recommended value 0.65 for fixed at both ends instead of 0.5. So evaluating this, that is equal to 68.78. So this is less than the limiting value. So that means the buckling is just inelastic. Okay, I will be using this formula. So 0.658 raised to Fy over Fe, and that Fe is the Euler buckling stress, or the elastic critical buckling stress. So that's pi squared E over the square of the slenderness ratio, the maximum slenderness ratio. So that is pi squared times 200,000 over 68.78 squared. And evaluating that, we can get 417.26 megapascal. So using that, FCR is 0.658 raised to 345 over 417.26 times the quantity of 345. And evaluating that, we can get 244.08 megapascal. And that should be the F that we're going to use in calculating for PE. Okay, that is not yet the actual flexural stress for that given column. Okay, so we're using that to get B sub E. So again, the formula for Q sub A is the effective area over the gross area, and BE has this formula for W shape, for a doubly symmetric shape, okay, I shape. So that's 1.92 T square root of E over F times the quantity of 1 minus 0.34 over B over T square root of E over F. We've solved F already, and T is the thickness of this web, okay? And this B over T is the H over TW that we took kanina. So it must be less than B. Okay, sometimes you could get a value of that greater than the B or greater than this H. This B means this H. So if ever this B sub A becomes greater than B, then we've got to use just B, okay? Or just simply make Q sub A equal to 1 if this BE exceeds B. So that B or H is equal to 351 minus twice of K, K design 19.9, and that gives us 311.2 millimeters. Then substituting the values of this, E is 200,000, TW is equal to 6.86, so that's it. F, we just took it kanina, 244.08, and this P over T is H over TW, okay, and that is 45.36. We got it kanina, the lambda W, square root of 200,000 over 244.08. And evaluating that, we can get this 296.13. That is in millimeters, okay? And as we can see, it's less than 311.2. So we must use that as it is, 296.13. Suppose if this becomes 320, then we must use 311.2. And with that, you just have to make Q sub A equal to 1 if ever this B sub A exceeds this. Okay, and since that doesn't exceed that, then Q sub A would be less than 1. So calculating for the effective area. So the effective area is like this. We are to reduce the area that is not included. It's like this. Wait. So the area would be the area of the flange plus area of this other flange, okay, plus this effective area at the web. So how to solve that? Well, that should be equal to the gross area minus this, okay? And this is equal to the difference of um, HTW and BETW. So we just have to subtract this, okay? So the gross area is equal to 5,710 millimeters squared minus HTW, that's 311.2 times 6.86 plus 291.13.60. The difference of these two, difference of this, as you can see, if you were to take the difference of this, 311.2 times 6.86 minus this would be the area na ito, okay? The area that is not being included. So continuing that, we can get an effective area equal to 5,606.62. Okay, that is now less than the gross area. So taking the ratio, the effective over the gross, that is the Q sub A. Okay, the reduction factor for the slender stiffened element. So the ratio is 0.982. And that should also be the value of Q, because QS, the reduction factor for the unstiffened element or the flange, is just 1. Why? The reason why it's 1, because that is short. That is too short. No, that is not too long, or that is not too thin. Okay, so it won't. It's not dangerous to local instability. It's not dangerous to experience buckling, local buckling. No, so that's why QA is just the same with a Q. No need to include a QS. So 0.982. So after that, use that 0.982 in calculating the um, the value of um, the length. I mean the slenderness ratio. Sorry for that. No, so the slenderness ratio would become this: 4.71 square root of E over QFY. I mean the adjusted limiting slenderness ratio for inelastic buckling. So including that Q 0.982. So the value of this becomes 114.44. And of course, the KL over R that we had solved kanina was 68.78, and that is still less than this. Okay? You may not check that if kanina we used the inelastic buckling stress FCR equal to 0.658 square raised to Fy over Fe times Fy. If we have used that kanina in solving for the FCR or the F at Q equal to 1, then that's what we're going to use pa rin dito, but with Q factor. So eto, that means there's no need to recheck this. Okay? There's no need to recheck. Why? Because the limiting value here would become greater than kanina. Okay, so it becomes more. This becomes more far from this. So ganun yan. That's why if we use this kanina, then that's what we're going to use here. If kanina we use, let's say, we use 0.877 Fe in calculating the FCR, that is for the elastic buckling stress, then that's what we're going to use here. Pa rin dito, no? So FCR is equal to 0.982 times 0.658 raised to 0.982, that's the Q, times 345 over 417.26 times the quantity of 345. So evaluating that, that's 241.18. Going back in the previous FCR that we took kanina, we got a value of 244.08, if you could remember. Okay, the value of F that we used to solve B sub E, that was 244. So as you can see, it's now reduced to 241.18, and that should be it. No, it must be reduced kasi dangerous ito sa local buckling. Okay, that's the purpose of the reduction factor. So the nominal strength is the product, of course, of the flexural stress and the gross area. Gross area yung gagamitin, of course, and that is equal to this 1,377,137.8. That is in newtons, of course, and making it in kilonewtons, that's 1,377.14 kilonewton. So that's it. That's the answer. That's the nominal compressive strength. Okay? So just follow this method. And of course, if we are asked to calculate for the LRFD design compressive strength and also the ASD allowable compressive strength of this column, then we're going to apply the reduction factor phi, which is zero point 0.9, right? So 0.9 times that Pn, that gives us 1,239.43. This must be greater than the required strength. The required strength for LRFD is 1.2 dead load plus 1.2 live load, if that is only involved or involving dead load and live load. Okay, and 1.4 dead load if there is no live load. So ganyan. And ASD allowable compressive strength, we just have to divide this by factor of safety equal to 1.67. Okay, so that's equal to the nominal strength 1,377.14 kilonewton divided by factor of safety 1.67, and that will give us 824.63 kilonewton. And this allowable compressive strength must be greater than the required strength for ASD. The required strength for ASD is the sum of the service dead load and the service live load. Just it, no, just the sum without factor. So this must be greater. If whether the sum of the service compressive dead load and service compressive live load must just be 800 or less, no, or 820 or less, okay? Or the factor 1.2 dead load plus 1.2 live load must be less than this. Let's say just 1,200. Okay, so ganun yan, in order for that to be safe. Okay, based on LRFD and ASD. So that's it. That's how to calculate the compressive strength for a wide flange or any I shape, S shape, HP, or M or W shape, that has a slender web. Okay, so just follow this method. So if you like this video, hopefully you'll click that like button, no, and you'll share this to your classmates, okay, to your timeline, so everybody would know that there's a channel discussing steel. And also, if you have not subscribed yet to my channel, please subscribe and ask to join in our Facebook group, the On the Real Solution subscribers, because I'm posting the PDF copy to this discussion and many more in my Facebook group. So thank you for listening. See you guys next time. Goodbye and God bless.